how to calculate triple integrals. Let's take now another example where I is equal to the triple integral of square root of x2 plus y2 plus z2 dx dy dz, where the domain omega is given by the region in space where x2 plus y2 plus z2 is less or equal than 4 and x, y, z are positives. In fact, x2 plus y2 plus z2 less than 4, that's a sphere. And since we have a sphere as in the domain and our function also has a spherical shape, it's x2 plus y2 plus z2, then first the domain would be like a part of a sphere because x is positive, y is positive, and z is positive. So that's why we'll go to spherical coordinates defined in this graph. So you have theta in the xy plane, phi is giving the angle with the z-axis, and r the radius from the origin to a given point. So r then will be between 0 and 2 because the radius of the sphere is 2. Phi will be between 0 and pi over 2 because we are taking only this part of the sphere, so the angle can be either 0 or it can go up to pi over 2 to cover all the points of the sphere. And theta as well should be covering from 0 to pi over 2 to cover this part of the sphere. So the integral can be written then as an integral between 0 and 2, that's for the r of course, and then 0 pi over 2, that's for phi, and then 0 pi over 2, that's for theta, or the other way around, because it happens that in this case that's 0 pi over 2 for both. And our function, that's square root of x2 plus y2 plus z2, so that's simply r, or square root of r2, that's r. Then I should multiply by the Jacobian. The Jacobian in this case, that's r squared sine phi. So I have finally the integral of r3 between 0 and 2, integral of 1 d theta between 0 and pi over 2, and the integral of sine phi between 0 and pi over 2. In fact, I'm able here to separate the three integrals because the function is separable. It's a function in r times a function in theta, which is 1 in this case, times a function in phi, and also because the boundaries are constants. So now all I have to do is to make some calculations. That's r4 over 4 between 0 and 2, theta between 0 and pi over 2, and then minus cosine phi between 0 and pi over 2, and the answer will be in this case 2 pi. Let's move now to the final example. That's the integral of x2 plus y2 dx dy dz, where the region in space, the domain omega, is given by all the points such that x2 plus y2 less than 1, so that's the circle in the plane, and then z is between 0 and some function minus x2 minus y2 plus 4. So if we'd like to draw this domain, it will be like we have the circle in the plane, and we take all the points inside the circle, even if they are above the plane or below the plane, but z is between 0 and something from top, which is the function, the surface that will cover the cylinder from the top. So we can see clearly that it has a cylindrical shape, and the cylindrical shape is very well to be treated with cylindrical coordinates, which are coordinates where z remains z and x and y are transformed into polar coordinates, which is nice because our function is x2 plus y2, so in polar coordinates that's r squared. So we go to cylindrical coordinates that are represented in this figure, and then z will be between 0 and minus r squared plus 4, r between 0 and 1, and theta between 0 and 2 pi because we have to make the full circle. We replace by r and theta and z in our integral, we get this form, the integral between 0 and 1 for r, 0 to pi for theta, and 0 minus r2 plus 4 for z. So we just integrate, we get r3z between the two boundaries, we replace, and then we get a function that can be separable, separated between 0, 1 for dr and 0 to pi for theta, and then doing a very simple calculation we can get to the result, which is 5 over 3 times pi. So these are the cases of triple integrals you might face.